Welcome back, everyone. Next up, we have ASP Isotopes, Inc. It trades on the NASDAQ under the symbol ASPI and is an advanced materials company dedicated to the development of technology and processes designed to produce isotopes used in multiple industries. They have an exclusive license to use proprietary technology, the aerodynamic separation process, for the production, distribution, marketing, and sale of all isotopes. Please welcome its CEO and chairman, Paul Mann. Welcome back, Paul.
Thanks for having me. It's great to see you. So we'll go through the corporate overview first of all, and then we can go to Q&A afterwards. So if you could just review these forward-looking statements, that'd be great. And we'll move on to the bulk of the presentation now. So what is ASPI and what do we do? Well, we're a company that can enrich isotopes for both the medical industry as well as technology industry, as well as the energy industry. We have two manufacturing facilities, both in South Africa. The first is operational. It started up about a month ago. The second will be operational around the middle of the year. And we have a huge backlog of demand from other isotopes from many different customers, both in the US and international. Historically, most isotopes have been produced by Russia. This has created a certain amount of uncertainty, the recent geopolitical events, and so a lot of companies and governments are assessing who their suppliers of such products are. In addition, one of the biggest isotopes sold in the world is Molybdenum-99. That's produced in 10 research nuclear reactors right now. 9 out of those 10 reactors are scheduled to shut down in the next 8 to 10 years, and so that creates a huge hole in the market, which we hope to fill as well. In terms of our facilities, they're very low in capital cost. They're quick to build, and we take a natural raw material and then we enrich it to what the customer wants. So I'll just move on to the next slide now. So what are isotopes? So isotopes are basically the same chemical, have different numbers of neutrons inside the nucleus, have a different mass, and we separate them according to weight or according to mass. And when you look at the picture to the right-hand side, these M&Ms, you can separate them by color: orange, green, and blue, and that's fairly easy to do using sight. We do the same, but by using different masses. So we enrich things, or we separate them out by mass. And if you think about some of our products we're going to be enriching, silicon-28, for example, for quantum computing. If I take a kilogram of sand, which is basically silicon, that costs maybe $1. If I take a kilo of silicon-28, that's about $600,000. So we take something that sells for $1 and something that's going to sell for $600,000. And then for carbon-14, a bucket of carbon, so call it charcoal, for example, is probably, again, maybe $1 a kilo. When we enrich that to 85% carbon-14, that's, $24 million a kilo. So again, we're taking something that's very cheap and we're turning it into something that's very valuable and highly specialized for certain industries. So that's what isotopes are, and that's what we do. Where are they used today? So there are a number of different industries use isotopes: the medical industry, the nuclear power industry, food irradiation, loads of different uses of isotopes around the world. But in the future, a number of new technologies that are emerging now will require new isotopes that aren't currently available. So quantum computing, as I mentioned earlier, will require large quantities of silicon-28. And we're the only Western producer, I believe, that can enrich silicon-28 to the levels needed for quantum computing. New advanced medical therapies and diagnostic procedures will require new isotopes like ytterbium-176 and nickel-64 that currently aren't produced by many Western companies. And new forms of fuel, satellites and spacecrafts are also going to require new isotopes that aren't currently available today. So why are isotopes interesting right now? And I kind of mentioned it in my opening remarks, but when you look at one of the bigger isotopes we intend to produce, Molybdenum-100, 9 out of 10 of the reactors will shut down in the next 10 years. We'd like to think we can get a share of that market. Also, as I said earlier, Russia is the largest supplier of isotopes to the world. So there's a huge concern right now, a serious concern right now about how companies and countries are going to manage to get isotopes that aren't currently supplied. currently supplied by Western producers. So the global kind of demand is at a kind of an inflection point in terms of producers and needs. In terms of the growth and demand, the isotope industry has been a fairly steady growing industry for the last sort of several decades. Historically, medical isotopes have grown at kind of 4 to 5% a year, so GDP plus a little bit. And then on top of that, there's a lot of new emerging uses for isotopes. So molybdenum 100 and molybdenum 98. There isn't really much demand for those right now, but we have customers wanting kilogram quantities as soon as next year, or actually later on this year. Ytterbium 176 and nickel 64, again, there's little suppliers of those, or no real suppliers of those outside of Russia. And again, we have customers interested in grams and kilogram quantities of both. And then I mentioned silicon 28, and there's a lot of new types of fuel for nuclear reactors and energy, and clean energy, such as uranium 235, chlorine 37, and lithium 6. And there's no kind of Western producer of any of those right now. So here's our kind of map of what we're hoping to produce or can produce already. And we'll go through each of these in a bit more detail later on in the slide deck. But we have one plant up and running already that can produce silicon 28 and carbon 14. And we have a larger plant of it coming on stream later on in the year that will be able to produce Moly 100 and Moly 98. And you can see there a list of other isotopes we're in discussions with customers about. And if I think about the future, zinc 68 is probably our next one. And then we've got ytterbium 176 and nickel 64, and then the energy ones at the bottom. But our technology is capable of enriching all of these isotopes. So the first isotope to be commercially available from our company will likely be carbon 14. That's a picture of our carbon 14 plant there. Those boxes, about sort of 2 meters 20 high by 2 meters long by 1 meter wide. That plant in that picture will produce the entire world's demand of carbon 14. Carbon 14 used to be sold exclusively by Russia. According to customers, Russia has been quite an unreliable producer of carbon 14. Some months it's available, other months it isn't available. There's been none available since February of 2022, and the world is in desperate need of a new supplier of carbon 14. We've signed an MOU with a Canadian group, so a North American group, who will be supplying us with feedstock, carbon 14 feedstock. We will then enrich it from 0.5% to about 85%, and we'll send it back to them. And that's going to be an extremely profitable contract for us, extremely valuable. That'll have a very high gross margin, and it'll be that plant's ready, up and running already. That plant started up in March of this year, and we're enriching oxygen right now in that plant. And as soon as our feedstock arrives in probably the second half of the year, that'll start enriching carbon 14. Carbon 14 is used by the pharmaceutical industry, the development of drugs and agrochemicals. It's used as a tracer to see how a chemical flows through the environment and through the ecosystem. Next up is molybdenum 198. The plant that can produce that will be substantially larger than the carbon 14 plant. Should be mechanically complete around the middle of the year, and we've signed our first contract for that plant already with a Chinese company called Brichem, which is the Beijing Research Institute of Chemical Engineering and Metallurgy. That contract is up to $27 million of product per year. That'll be highly enriched molybdenum 100, and they will use that to convert into molybdenum 99 or technetium 99 in China. The molybdenum 99 market, as I mentioned earlier, is a $3.5 billion market. It's currently produced in these 10 nuclear reactors around the world. And Moly 99 has a half-life of just 66 hours. So it's halving in value every 2.5 days. So the supply chain has been extremely complex, fraught with frustration and problems over the last 20 years. Countries are regularly running out of supply. The world, in our view, needs a better source of molybdenum. We feel molybdenum 100 is stable, shelf stable. You can keep it, an inventory of it, and essentially you can convert it to technetium 99 at the point of care. bit like popping something into a microwave. You just turn it into the finished product at the point of care, and it will save a lot of the supply chain issues which you're seeing right now. Finally, silicon-28. We've produced silicon-28 already, up to 97% in that small carbon plant. That carbon plant isn't big enough to produce commercial quantities of silicon-28 at the kind of levels of enrichment that our customers we're talking to need. So our molybdenum plant probably can do silicon-28. We may build another plant. We'll see how contracts come out over the next sort of couple of months. But for quantum computing to work, people are going to need silicon-28 enriched to 99.995%. And when you think about silicon, there's 3 isotopes of silicon, and 28 and 30 kind of both point in this direction, and 29 kind of points in that direction, and it blocks the current. When you remove that 29 isotope, you improve the conductivity by hundreds of fold. So for advanced semiconductors and quantum computing, this is going to be what is, what makes an industry work. And again, I think we're the only Western company that can enrich silicon-28 to that kind of level on a commercial scale. And we're talking to a number of potential customers about silicon-28. Finally, just talking about some of the energy opportunities. Uranium is becoming interesting again for a number of reasons. Russia's responsible for about 40% of global uranium enrichment. The United States currently imports about 90% of its uranium requirements. These supply about 10% of US electricity. Many countries have realized that the only way we're going to reach 2050 climate goals is by increasing the amount of nuclear power. It's the only real energy source that can provide a base load of energy or electricity to a community. You'll see on the right-hand side of this slide here a number of actions that governments are taking to try and increase its mix of uranium, of nuclear power in their countries. In terms of the future of nuclear power, we firmly believe it's a small modular reactor. There are a number of companies involved in building these. X-Energy and TerraPower are probably the two leaders in that race. The US DOE's put about over $4 billion into these programs over the last several years. And these are small modular reactors that allow small cities or small communities to generate all their power they need from nuclear power. Anywhere in the world, you can get power at sort of 3.5 to 4 cents per kilowatt hour, which is a very low cost of energy for most parts of the world. And there's a number of countries looking at deploying these. These all use a different type of uranium to what's currently used in nuclear reactors. Most nuclear reactors today use low enriched uranium, which is up to 5% of the 235 isotope. These are going to require high affinity low enriched uranium, HALEU, which will be up to 19.75%. Right now, there is no Western producer of HALEU in quantities required for these nuclear reactors. TerraPower recently delayed its startup of its first reactor by a few years because it can't get HALEU. And the US DOE recently put together a $700 million kind of proposal to try and accelerate the development of HALEU, domestic HALEU production in the United States. This isn't the kind of project we're going to do by ourselves. We're talking to a number of companies and governments about potentially building such a plant. We think our technology is viable for this process. And at the bottom here, you'll see the kind of stepwise process in kind of doing it. This is a huge, very different regulatory regimen to where we operate right now. This will take several years to build out, but obviously the need is there, and it's a huge potential opportunity. This slide just shows a couple of other opportunities we're talking to customers about. Zinc-68. I think we'll probably end up building a Zinc-68 plant in the next couple of years. Likewise, chlorine-37. Zinc-68 is becoming an important radioisotope for production of both copper-67 and gallium-68, and both of these are used in either oncology or the diagnostics industry. Chlorine-37 is going to be required for molten salt reactors, which should start to come on stream around the end of this decade. The world's going to need 20 to 40 metric tons of chlorine-37, according to these companies. And I believe we're the only Western company capable of producing chlorine-37 in those kind of quantities. Lithium-6 is going to be required to enable nuclear fusion. You mix lithium-6 and deuterium together, and again, there's no Western producer, no Western enricher of lithium-6 or lithium-7 for that matter, and that's right in our sweet spot. That's something we can do fairly easy. We're talking to many governments and companies about lithium-6 and ytterbium-177. It's a new emerging oncology treatment. So, in terms of how we set the company up, these smaller plants like Moly-100, carbon-14, zinc-68, lithium-6, 28, we can build those plants ourselves. Those plants typically cost $10 to $15 million to build. Cash-on-cash payback is 2 to 3 years. High gross margins, good small base of customers. They're the kind of plants we expect to be able to build ourselves. Larger plants such as HALEU, large lithium-6 plants or chlorine-37, they're the kind of plants we're more likely to partner with, as they're much bigger opportunities, and they're vastly different in terms of size. So, just in terms of concluding remarks, we have a proven technology platform. It's environmentally friendly. We're able to produce many different types of isotopes. It's highly competitive and it's modular, so we can grow plants as demand grows. Doesn't require a huge amount of capital, very fast construction times. The isotope industry has been a very long-term secular kind of grower over the last 20 years. Recent geopolitical events are making governments question where they get their isotopes and products from. Our first isotope plant is operational. It started up in March of this year, and construction of our larger plant should conclude around in the middle of the year. Both plants should enter commercial production during the second half of this year and should drive considerable amounts of free cash flow. And as I say, we've got a huge backlog of interest from other customers for other isotopes. So I'll stop there and I'll take any questions.
Great job, Paul. Okay, we do have some questions for you. A question from Lou Daniels. Lou wants to know, who is your closest competition, and talk about how you are better.
So in terms of competition, it depends really which isotope you're talking about. But I would say in general, isotopes are typically enriched by government entities. So people like Urenco, Rosatom, Chinese nuclear, those kind of entities. We're probably the only non-government enricher of isotopes that uses centrifuges today, a commercial producer of isotopes today that uses centrifuges. So, in terms of our main competitors, I've kind of just mentioned them. And what makes our technology better? I think we have a very low capital cost to build plants. We can build plants quickly and efficiently, and we can also enrich light isotopes as well as heavy isotopes. So large centrifuges can only enrich isotopes to a mass over 100, whereas we can enrich isotopes right down to a mass of 2. And so for light isotopes like chlorine-37, silicon-28, lithium-6, deuterium, zinc-68, all those isotopes are perfect for our type of technology where we can just enrich those low masses. So I guess that probably I hope that answers that question.
That's a great answer. Adam W. wants to know, how are you getting your customers? Talk about that, including the industries you're focused in.
Yeah, so actually, let's take our molybdenum plant as an example. We have had interest for about 4.5 times as much capacity as we can actually produce. And so, customers kind of know who we are. We haven't actually made a single outbound sales call. We don't have any salespeople right now. All the demand has been incoming demand. And I say we've had a number of phone calls from many different companies involved in many different industries. Now, the industries I really like as our first isotopes are the healthcare, medical isotopes, and medical isotopes, and medical isotopes, and for technology, things like silicon-28. But yeah, I mean, it's a pretty unique marketplace.
I bet it is. Jim Brown wants you to talk about your growth strategy for financial and your geographical reach.
So most of our isotopes right now, we're going to be producing in kilogram quantities per year. So shipping these isotopes around the world is pretty straightforward. So in terms of reaching customers in different geographies, it's very easy to ship these products in using standard shipping methods. It can be very expensive, but you can get insurance for that. In terms of where we build future plants, it's unlikely we'll build any more plants in South Africa. Our first 2 plants are in South Africa. I think we'd like to build our plants in a location that has cheaper, greener energy. And we're talking to a number of countries about potentially building plants there. So, yeah.
Kurt wants to know how you compete with Eastern producers like Russia on a cost to produce and profit margin basis.
So Russia doesn't, Rosatom doesn't supply any financial statements. So it's difficult to know how we compete on a cost basis or a profit margin basis. But talking to most customers or potential customers, the kind of price ranges we discussed with them, it hasn't been a problem for us to meet those kind of prices that the customers are requesting. And in some cases, these are hundreds of dollars per gram in many cases, or thousands of dollars a gram. And so again, they're very specialized products.
And so William wants to know, when you're talking about isotopes for lithium, is your market for this battery makers? And if so, any majors buying from you now? Yeah,
so we don't produce any lithium right now. Lithium-6 is an isotope we'd like to produce in the future. It's unlikely to be used by battery manufacturers. Battery manufacturers just want normal lithium. Lithium-6 has some very special properties that can be used for nuclear fusion. And, we believe we can enrich lithium-6 to the kind of levels that the nuclear fusion companies want to go to. And so that's more likely the end market for lithium-6. And it's more likely next decade, not this decade, or maybe towards the end of this decade. It's not something we're doing the next sort of 1 to 2 years. And so if you looked on that map earlier I provided, that had one of the shorter arrows, as in we're technically capable of doing it, but it's unlikely as a plant we're going to build in the next 12, 18 months.
And Trevor McLaughlin asks, regarding producing in the U.S., what are any environmental hurdles you're coming upon?
So we don't have any plants in the United States. It's unlikely that environmental permits will be a big problem here. We don't really have any waste as such. We think about it, we take 100 kilograms of a gas, we put it through our plant. We take maybe a kilo or 2 of highly enriched gas, and 98 kilos of the gas is virtually unchanged. I'm going to sell that straight back to the marketplace again. So it's not like we've got any co-products or waste streams. So environmentally, these plants aren't big polluters of anything. And there's no, we don't really consume lots of water or have large kind of fumes or pollutants. So environmental permits are unlikely to be the gating process in any country. We do have to operate under the Non-Proliferation Council and under the International Atomic Energy Agency. So in terms of regulatory constraints, our biggest regulatory constraints are more from the nuclear regulators than they are from environmental regulators. I say we're controlled and regulated by the Non-Proliferation Council and the IAEA.
Perfect. And Dan wants you to talk about your margins on the different forms of isotopes.
So, most of our margins are going to be, well above 50%. Some approaching 80 to 90%. So it depends a lot upon which isotope. and the customer specifications. Some customers may want particularly highly enriched forms of isotopes in a particular form, like a metal. Others may want less enriched as an oxide or a powder or something. So it depends on exactly what specifications the customer provides. But think about always better than 50%. Many of them approaching 80 to 90%.
And can you talk about your growth rate over the next 24 months? Omar wants to know.
So right now we have no revenues and we have no profits. So we're starting from a baseline, but we've signed one contract for up to $27 million of revenue a year. We're negotiating many more. It's my belief that we'll probably sell out both our first two plants, the carbon plant and the molybdenum plant. And so that will bring substantial amounts of revenue and free cash flow into the company. And that revenue will start up, around the end of this year, beginning of next year, depending on the timing of when the first deliveries are made.
And Rod wants to know, is there anything you cannot do with a centrifuge that the market might demand?
There are some isotopes we cannot enrich with a centrifuge, and some it may not be economically viable to do with a centrifuge. So first of all, a centrifuge has to operate with a gas. So if you can't turn can't turn an element into a gas, it won't work in a centrifuge. And then some isotopes, very few of them, have different boiling points or melting points, and so you can separate them thermally rather than having to use a centrifuge. So and that's probably a cheaper way of doing it. So oxygen, for example, and hydrogen, deuterium, but most of the kind of the bigger isotopes like silicon, zinc, molybdenum, they're gaseous compounds of those, and they're kind of perfect for us.
From Mike Strickland, he says there's a massive semiconductor plant being built in the U.S. in order to defer manufacturing from Taiwan. So his question is there an opportunity for you there for your business or government funds?
So as I said earlier, our plants are small in footprints, and that large semiconductor factory that he's talking about will consume kilogram quantities of the kind of products we may produce, or may consume kilogram quantities of the products that we may produce. And so there's no reason why one of our plants has to be co-located or located close to the customer. We're actually better off putting our plants in a cluster, so we have a number of plants together in the same location, for a number of reasons, but mainly because of the regulatory and control reasons. Anyone entering our plant, our plants are highly controlled and regulated by the Non-Proliferation Council. Every person entering our plant has to go through a very strict security check. Only certain people are allowed to operate them and work within them. And so it's together in the same location, where they can come under the same regulatory guidance and scrutiny.
And we have our last question from Carter Hollander. Carter says your chart, he saw the chart where you saw where the next isotopes are to be produced. So can you give a timeline on the start of the production and entrance into sales in that space?
So we've not given any formal guidance on revenues or profits yet. But what I have said is our first two plants will be starting up and producing second half of this year, hopefully. And we fabricate most of the equipment ourselves for our plants. We have a construction crew that builds plants, and so it'd be nice for them to roll straight off the construction of our big plant onto another plant. So hopefully we'll start building that pretty quickly after we finish these ones. So could that plant be up and running in 2024, 2025? Quite possibly, yes. My prediction is that any plant we build will be sold out on day one of product.
Well, that's a good problem to have. All right, Paul, do you have any closing remarks for us?
Yes, thanks very much for your time today. Thank you for the questions. I say, we're please feel free to look at our website and follow us for more news. And hopefully a lot of news flow coming over the next 12 to 18 months as we finish these plants off and go into commercial production.
Wonderful. All right. Thank you so much for joining us on the Emerging Growth Conference, and we would love to have you back with some updates.
Yeah, thank you. Bye.
Okay, everyone, we will be back at 12:35 for our next presenter, so join us very shortly. We'll be back.